This is Porterville College, Physics 104A, Chapter 6 homework, starting with number 11. Work equals force times displacement, so 75 newtons times 12 meters equals 900 joules. For number 19, you apply a 470 Newton force at 17 degrees to the car's motion, doing 860 joules of work. How far do you push the car? So here's the vectors of displacement and force with a 17-degree angle between them. Work equals force times displacement times the cosine of the angle between the two. So when we solve this for displacement, we get displacement delta x equals work over force cosine theta. We plug in those values and we get a displacement of 1.9 meters. Number 21. Excuse me. Okay. Number 21. How much work does it take to stretch a spring 10 centimeters from equilibrium and from 10 to 20 centimeters? Okay, here's the work formula. 1/2 kx2 squared minus 1/2 kx1 squared, and I've factored out the 1/2 k. So for part A, x1 becomes 0, and so if I block this out with my pen, it just becomes 1/2 kx squared. So here it is for part A, 1/2 times 200 newtons per meter times 0.1 meters squared, and you get 1 joule. Now part B uses this full equation, 1/2 k times x2 squared minus x1 squared. But now instead of x1 going to 0, x1 is 0.1. So we have 1/2 times 200 times 0.2 squared minus 0.1 squared. And we get 3 joules. What I've done here in blue is I've derived the work equation that's at the top. So in case you're wondering where it came from, work is the integral of force with respect to dx, taken from x1 to x2. Next is number 39. It takes 20,000 joules to melt an ice cube. Typical microwave produces 900 watts. How long will it take to melt the ice? So we need power equals energy over time, which means time is energy divided by power. So we have the energy that it takes, 20,000 joules, divided by 900 joules per second, and we get 22 seconds. Number 45. You pull 23 meters horizontally. If the rope tension is 120 newtons, and the rope does 2,500 joules of work, what angle does the rope make with the horizontal? Okay, so we have work equals force times displacement times cosine theta. We're solving now for cosine theta equals work over force and displacement, which means theta will be the arc cosine of work over force and displacement. So arc cosine of, you plug in those values, and which that becomes arc cosine of 0.905797, and it comes out to be a 25-degree angle. '47 is some practice with vectors. So we're doing the dot product of these two vectors, and I've written them out in my stacked vector notation, ai hat plus bj hat, and this is bi hat minus A j hat. Dot product is the product of the x values, so A times B, plus the product of the y values, B times negative A. So AB plus negative AB becomes 0. Now we want to know the angle between them. So it's useful to do this. First of all, I've just drawn the picture. Hold on. Yeah, I've drawn the picture this way, and we get the dot product of A times B is AB cosine theta. So we want to solve for cosine theta. Cosine theta is the dot product of A times B divided by the product of the magnitudes A and B. And we know that it's equal to 0 because we solved it up here. So cosine theta equals 0. And then we think, what angle has a cosine theta equals 0? And that's 90 degrees. I just, a minute ago, I stalled as I was pointing out this picture because I realized what I actually did was I just drew this vector times this vector without regard to lowercase a's and b's. I did I plus j hat and I minus j hat. So actually this picture that I've drawn isn't to scale, but still it does display the correct angles, or the correct angle. Okay, number 49. How much work does a force given do as it acts on a body moving in a straight line from R1 to R2? Okay, so work is the dot product of force and displacement. So here's force. I've written it in my stacked vector notation, 67, 23, and 55, I hat, j hat, and k hat, times displacement is R2 minus R1. So I've written that all as one vector. Here's R2, 21, 10, 14, and we're subtracting 16, 31, and 0. So when you subtract 21 minus 16, we get 5 for the x direction. 10 minus 31 in the y direction gives negative 21. And 14 minus 0 is 14 in the z direction. So in this line, the first vector is the force vector, the second vector is the displacement vector. When we take the dot product, we do 67 times 5, plus 23 times negative 21, plus 55 times 14. And the units will be newtons meters, which is joules, so we get an answer of 622 joules. Number 50. Force is given by 5x squared. It says in the x direction, so it's the vector is 5x squared I hat. Find the work done as it acts on a particle moving from x equals 0 to x equals 6. Okay, so work is the integral of force dx evaluated between the two x's. So that becomes integral evaluated between 0 and 6 meters of 5x squared dx. So when we take that integral, that's 5/3 x cubed evaluated from 0 meters to 6 meters, and you should get 360 joules. $55. Two unknown elementary particles. They have the same kinetic energy, and their mass ratio is 4:1. What is the ratio of their speeds? So, let's make some equivalences here. I call one particle 1, the other particle 2. So kinetic energy 1 equals kinetic energy 2. It doesn't say which one is 4 times the other, so I've just arbitrarily said the particle number 1 is the heavier one, so m1 equals 4 times m2. And I want to know what is the ratio of v2 over v1. So let's start here with the statement that their kinetic energies are equal. That means that 1/2 m1 v1 squared equals 1/2 m2 v2 squared. Right away I can divide out those 1/2s. And I'm also going to replace, instead of m1, I'm going to go over here and substitute for m2. So now this m1 is 4m2 v1 squared equals m2 v2 squared. And right away I can divide out m2's. And I'm left with, I'm on this line with the things in red gone. It says 4v1 squared equals v2 squared. So get the v1 squared over to the right hand side by dividing by it, and we're left with 4 equals v2 over v1 squared. Take the square root of both sides, and you get the ratio of their speeds, v2 over v1, which is what I set out to solve in the beginning, is equal to plus or minus 2. Number 69. A machine does work at a rate given by P equals 18t squared. Find the work done between 10 seconds and 20 seconds. Okay, so work is the integral of P dt. So let's plug that in. Work is the integral of 18t squared dt evaluated from 10 to 20. So we take that integral, and we get, I've moved the 18 out to the side, so 18 times and then 1/3 t cubed, and that's going to be 6t cubed, evaluated from 10 to 20. So 6 times 20 cubed minus 10 cubed, and I get 42,000 joules. Number 77. So we have this recognition that work is the integral of f dx. We plug in the force, and we have to think about what are our limits of integration. It says that it normally has a length of L0. So let me draw this here. It normally has a length of L0, and normally means that's its equilibrium length. And then we're going to double its length. Bring it from here to here. So this is equilibrium. So we'll call equilibrium x equals 0. When it's stretched out all the way, it's going to be L0, because it's doubled its original length. It's going to be L0 in addition to 0, so it's going to be L0. So these are our limits of integration from 0 to L0, because we define x as how far from equilibrium it is. So integrating from 0 to L0, there's our force, dx. You do the integral however you do it, however you do integrals. Here's how I do it. First, I've just taken that negative sign and thrown it out to the side. And I've just done each of these separately. Kx, then bx squared, then cx cubed, and then dx to the fourth. And you might just treat it all as one integral, that's fine, but it does, whether you write it or not, it does break down to these 4. So each of them becomes 1/2 k x squared, 1/3 bx cubed, 1/4 cx to the fourth, 1/5 dx to the fifth. And in this line, I've already plugged in the limits of integration. So I've plugged in L0. And then what I haven't written off to the right, where my pen is, what this could say is minus all those terms with 0 plugged in, but they would just all go to 0. So this is the work done by the cord when it's stretched. But the question is asking, hold on, a formula for the work involved in stretching the cords. So we want to know what is not the work done by the cord, but what is the work done to the cord. And it's going to be just the opposite of that. So you can just take this negative sign, get rid of it, because we're taking the opposite, and so the work done to the cord is right here, my part A answer. 1/2 k L naught squared plus 1/3 b L naught cubed plus 1/4 c L naught to the 4th plus 1/5 d L naught to the 5th. Question B says evaluate the work done in doubling, and it just gives the particular numbers to plug in. And so when I plug in those numbers, I've done the intermediate values along the way, so you can check your work if you get something that doesn't agree with mine. So the part that involves K, I got 21,000 joules. The part that involves B, I got negative 28,667 joules. The third part involving C, I got plus 30,000 joules. And the fourth part involving D, I got negative 10,000 joules. Add them all together, and it comes out to 12,333 joules. But we'll do significant figures, 12,000 or 12,000 joules or 12 kilojoules.